Hello students, in this video we are going to discuss about demand paging, which is one of the memory management policies. In the previous video we discussed about swapping, um, where some pages are swapped in and swapped out based on the need. Here in this video we are going to discuss about demand paging. So what is demand paging? Demand paging means loading a page on demand, that is called demand paging. So as we discussed, the primary memory is one of the precious resource. So primary memory has to be utilized more efficiently. So generally in our system, the primary memory will be lesser when compared to our secondary memory. For example, if my system has primary memory, that is RAM of size 2 GB, then my hard disk could be of size 500 GB. So I can't store everything on my 2 GB of RAM. So whatever process on demand, whatever process I have to execute currently, only such process will be loaded into my RAM and then it will get executed. So how it is possible for us to execute a game which is of 5 GB or 4 GB of game in a RAM of 2 GB? Or for example, if I have a program of 5 MB but my primary memory size is only 2 MB, I'll be still able to execute my 5 MB program in my 2 MB RAM. It is possible. So such things are possible only through demand paging. So demand paging makes it possible by dividing the entire process into pages. Pages means it is equal size blocks, and it will load the necessary pages into the memory, and the remaining parts will not be loaded into the memory, and such parts, the remaining parts, will be loaded into the memory on demand. So that is called demand paging. So in this example, so in this introduction, let's see about in more detail about demand paging. So demand paging systems free process from size limitations. So we don't have any size limitations to execute a program. So as I already quoted an example where we can execute a game of size 5 GB in a RAM of size 4 GB. So the game will be divided into pages, and the necessary pages will be loaded into the memory, and then other pages will be loaded on demand. So the kernel must load relevant portions into memory dynamically and execute it even though other parts are not loaded. So even though other parts are not loaded, still the program can get executed. So the process tend to execute instructions in small portions of their text space. So not all pages of process resides in memory. As I told you, not every pages will be loaded into the memory. Other pages will be available in your secondary memory, and whenever it is on demand, it will be loaded. The secondary memory is a swap device here. So there is a concept here, as we might have heard about this concept, that is principle of locality. So principle of locality means, so what are the recently used pages or recently referenced memory, so that has to be stored inside our in our primary memory. So that is called principle of locality. For example, if I'm executing a program where the program is having a loop, so the loop has some 10 instructions. So the 10 instructions will be executed again and again. So maybe the 10 instructions has some memory references, and it is loaded in different memory locations. So such the 10 instructions are going to execute it again and again. So it will be good, it will be beneficial if that 10 memory pages are loaded inside memory. And if that 10 memory pages are not loaded into the memory, and if it is getting removed after every execution, every time when it has to get executed, it has to copy from the secondary memory to the primary memory. So it will the computational cost will be high, and the program will take a longer time to get executed. So that is why the principle of locality means program tend to reuse data and instruction that they have used recently. So with this idea, we can keep the recently used memory pages or recently referenced memory pages in the locality, that means in the primary memory itself, so that once it is recently used, if we are using it again and again, instead of copying it from the secondary memory, we can access it from the primary memory itself. whenever that particular page is old or particular page is no longer referenced, at that time that particular page can be swapped out and the new page can be swapped in. So whenever we are expecting a new page, when a process accesses a page that is not part of its working set, that means something called as working set here they are discussing about. So working set means what are the pages currently I'm using, currently what are the pages are loaded into the primary memory, and how what are the pages which is relevant to that particular executing process, that is called as working set. So whenever a process wants to access a page which is not part of the working set, that means currently it is not available in your primary memory, and then at that time it incurs page fault. So page fault means a process trying to access a page which is not available in the primary memory. So at that time it incurs a page fault. Whenever a page fault occurs, page fault happens, the kernel suspends execution of the process until it reads the page into the memory and makes it accessible to the process. So the process will go to sleep, and then it has to access the page which is not available in your primary memory. It has to be loaded into the memory, and then the process resumes. So in this example, let's see what are the sequence of page references whenever during a course of execution of a program, and these are called working sets and window sizes. Different window sizes are mentioned here. So each and every program, every system may have different window sizes. So in this example, the first one represent 2 window size, second one represent 3, 4 and 5 window sizes sequentially. So these are for different systems. So some system may support 2, some system may support 3 window size, some system may support 4 window size and 5 window size. So window size is nothing but how many pages at a time it can be loaded into the memory. So if it is 5, if window size is 5, that means 5 pages can be loaded into the memory at a time. And if it is 4, 4 pages can be loaded into the memory. If it is 3, 3 pages, and if it is 2, 2 pages. And these are the execution, how a program is getting executed, and which are the pages are referenced during the execution of a program. So these numbers are representing the different pages which are referenced during the execution of a program. So let's see the first example, 24. So 24 is a page which is required, which is currently on demand. So in the working set, maybe initially the 24 is not available in all these cases, 2, 3, 4 and 5 in all these window sizes, 24 is not available. So 24 is loaded into the memory, it is on demand, so it is loaded into the memory. And then in the next page reference, so 24 is getting executed, and then the 15 is demand. So 15 is loaded from the secondary memory, that is from the swap device. So actually if the window size is 2, then it's already full, that working set is already full. So working set is currently 15 and 24. So these are the 2 pages which is considered as a working set, and which is currently associated with the executing process. In this working set, window size of 3, only 2 pages are available, still I can store one more page, and in window size of 4 I can still store 2 more pages, and here 3 more pages. The next one is 18 pages on demand. So 18 pages not available. If you consider this case, so 18 is not available in this working set, it is only 15 and 24. So one page has to be swapped out. So the least recently used algorithm is used here. So least recently used algorithm, 24 is least recently used, 15 was recently used, 24 is least recently used. So this page will be swapped out, and the new page 18 is swapped in. Okay, so in the next window size, so still here we had size of one page can be loaded, so 18 is loaded, here also 18 is loaded, and here also 18 is loaded. And then we are trying to reference, the process is trying to reference the page number 23. So 23, once again we are checking here in the working set if it is available or not. It is not available, so least recently used algorithm is used to swap out the page. So 15 is the page which is least recently used, and 18 is the page which is recently used. So 15 is swapped out and 23 is loaded. So here, but in this case, if once again in the third 3 window size we are checking, here also 23 is not available. As per this window size, we have 3 pages, so any one page has to be swapped out. So 18, 15 and 24. So 24 is least recently used, so this page will be swapped out and 23 will be swapped in. And in here we had space, so 23 is loaded, and here also 23 is loaded. And then next in this case, So 24 is expected. So 24th page, which is already referenced in the beginning. So once again, this process is trying to reference the same page. So once again, this page is not available here. That has to be swapped out. Some process has to be swapped out. Page has to be swapped out, and it has to be swapped in. Here also that page is not available. But here, if you see, 24 is already available. So this window size for window size 4 and window size 5, we don't need to copy the content from your secondary memory. Rather, the content is available in your primary memory itself. That means in the working set itself. So this will reduce the page fault, and whenever it is reducing the page fault, it is improving the efficiency also. So the higher the window size, the process efficiency will also be high. So whenever a particular page is required and if it is not available in your memory, that inquires page fault. So whenever page fault occurs, we have to use least recently used algorithm to swap out a old page and to swap in a new page. So that is what the operation of demand paging. So let's see some of the details about demand paging. That is, what are the data structures for demand paging? So how these details are going to be maintained for demand paging? That is by using page table entry, disk block descriptors, page frame table data table, and swap use table. So these are the four data structures are used for demand paging. So these four data structures are going to maintain the records details about the pages which are going to be referenced and which are going to be swapped out and swapped in. So this is a data structure description or data structure visualization. So every process will have a region, and then we have a page table for every process. So the page table will have two entries. One is page table entry, another one is disk block descriptor. So what is the page table entry will have the information like page address, so where the page is located, the age of the page. Age means how long that particular page is spending the time inside the primary memory. So whenever the particular page is not referenced, then the page age of the page will be incremented from 1, 2, 3 like that. So this is copy on write. This is a flag which has to be set, that is copy on write. This is mode, and then with this reference, validity, and protection bits. So these are the different bits we have for this page table entry. Then for disk block entry, we have swap device, swap device number. Swap device number means more than one swap device may be available in a system. So which swap device it belongs to, and which block number it is presenting in. Block number is like the direct block, indirect block. So in which block it is available, and what is the type of the block. So these details are maintained in the page table entry and the disk block descriptors. So the page table entry in detail so contains the physical address of page and the following bits. So we have a valid bit here, whether the page content is legal or not. If the valid bit is 0, that means the content is not legal. If the valid bit is 1, that means the content is legal. So reference, whether the page is referenced recently or not. So based on that recently used algorithm, that the page will be referenced. And modify bit will be set if the page content is modified. So this is required whenever you want to update the content in the swap device. And then copy on write, the kernel must create a new copy when process modify its content. So this is required whenever we are executing a fork system call. Sometimes fork system, whenever we are executing fork system call, the parent data may not be copied to the child, but it will be just incrementing the reference region reference count. So in some cases, if it is mentioned as copy on write, whenever we are making a modification, a new copy has to be created. That is copy on write bit, and then age of the page, how long it has been not referenced inside the primary memory, and protection bit, it is read and write permission. Then we have disk block descriptors. Disk block descriptors, as I already told you, it is swap device number. There are maybe several swap devices available, and block number contains page number, and the type specifies the swap, the file, or fill 0, demand fill, or demand 0. So we'll discuss it in more detail. So next one is page frame table, page frame data table. That is also one of the data structures of demand paging. So which describes each page of physical memory. The page state, what is the state of the page? on swap device or executable file, or the page can be reassigned or not. Then page number of the process that reference the page, the reference count will also be maintained by this page frame table. And then logical device and block number, which is required for each and every page, where it is located, where in which block it is located, and pointers to other page frame data table entries on the list of free pages. So all these things are going to be maintained by the page frame data table. So this is the relationship of data structures, how it is going to be referred. So we have this page table entry and disk block descriptor. So page table entry will have this page number, and the physical page number will also link to this page table entry. Disk block descriptor will have the swap device number and in which block it is available. And here the page frame table maintains a reference count, swap device detail, and block number. The swap use is another data structure which is going to maintain the reference count for every page. So reference count is very important here. So based on the reference count, whether the particular page needs to be swapped out or swapped in, that can be decided based on this reference count. Then the swap device, block, and all the details. So this is what the relationship of data structures. So what are the situations this demand paging is required? So when are the situation is required? So here we are going to discuss about two situations. One is fork in paging system, another one is EXEC in paging system. So whenever your system supports paging, that means demand paging. That whenever we are executing a fork system call, the process may not be loaded into the primary memory, but it will be loaded into the secondary memory. And once there is a space, once it is on demand, then the child process will be loaded into the primary memory, and then it will get executed. So this is a visualization of execution of a parent and child process. So initially this is a parent process. Process P is parent, and process P has regions, that is text region, and this is private region P1. It has two regions. And when the process executes a fork system call, it creates a new process, that is process C. So process C is created, and the text region for process P is shared with process C. So you can see the reference count is incremented to 2. Instead of copying a new region, the reference count is just incremented. So that means the process C is referring this particular region. And then we have there is no change in all the page frame table and other things. But here if you see, there is another private region which is created for process C, and that will be loaded inside your in your secondary memory, and whenever it is on demand, that particular page will be loaded, and that is why we have this page frame count, reference count, and other things. And based on this, the page will be loaded into the memory, and then it will get executed. EXEC is another process system call that is going to load a new process or execute a new process whenever we are using this EXEC system call. So kernel reads the executable file into memory from the file system. That means whenever we are using EXEC system call, the already occupied memory has to be freed, and the new memory has to be allocated. That means new process has to be loaded and it has to be allocated. So assigning memory as needed, and then kernel finds all the disk block numbers of the executable file. So whatever file we are going to execute, load that particular file's information will be loaded. So the next topic is Pagestealer process. So Pagestealer process was one of the important process in demand paging. We know demand paging, we need to load the memory with pages, and sometimes, or whenever on demand, some pages has to be captured and some page has to be swapped out, and the new page has to be swapped in on demand. So which process is responsible for swapping out a process? So how can we decide a process? How can we decide that a page is old or the page is not necessary right now and the page can be swapped out? So that can be decided by using this page table process. So Pagestealer process. So Pagestealer process is one of the important process. It is a kernel process that swaps out memory pages that are no longer part of working set. So as we know, there are working set, the window based on the window size of 2, 3, 4, 5, based on the system configuration. If the working set is 5, and if there is no room in the working set, and new page has to be loaded inside. As we already know, we are using this least this recently used algorithm to swap out the process, and that will be done by this Pagestealer process. So the kernel invokes Pagestealer process when the system is low on free pages. That means when there is no free pages available on the system, then the Pagestealer process will be called, and then it will steal the pages which are old inside the memory, and it wake up when free memory is below low watermark. So that is a threshold set for a page stealer process. So when the threshold is when reached to the lower mark, then the page stealer process will wake up and it will swap out the process which are older, which are aged, and when it reaches the higher watermark, it will go to sleep again. So swapping out until exceeds the higher watermark. So it will swap out all the process uh, which are under the lower mark when it is under the lower mark. So this is a figure for page stealer process. So this is the page, this is the page in memory, and these are the pages out of memory. So whenever a page is loaded into the memory, initially it may be executed, and then when it is not referenced recently, then it will be in the age of the page. This pages will be, the age of the page will get increased. If the page is currently under reference, that means if the page is currently under execution, the age of the page is 0. And when the page is not referenced recently, then each and every time the age of the page will be incremented from 1 to 3. So 3 means that particular page is older than the page of 1. That means if that page stealer process is executing, it can steal this particular page and it can swap out the page. So this n is the threshold value which is set. N is the threshold value or the lowest mark. When it reaches this particular value, that particular page will be swapped out, and then the new page can be swapped in. So this is what the page stealer process is doing. So this is the example of aging of a page. So in memory, this is a process in memory or page in memory. When it is currently executing, the age of the page is 0, and this is, if it is not referenced, that means if it is not executing, then the age of the page will be increased 1, 2, and then once again the same page is referenced, refer, and that time the age will be reset to 0. Then when it is not referred, it will be incremented. When it is referred, it will be incremented to 0. And so here it is 3 is the watermark, or 3 is the maximum age for a page. So when it reaches 3, that particular page will be swapped out and new page will be swapped in. So that is what aging of a page. So there are three possibilities when page stealer process swaps out a page. So no copy of page is on swap device. So we know we have a swap device, that is a secondary memory, and there is a primary memory. So whenever a particular page has to be swapped out, or the page stealer process is swapping out a particular page, it will check whether the copy is available in swap device or not. If the copy is available, then we can just remove the content from your primary memory, and we can maintain the secondary memory copy. But here there are three possibilities available. The first possibility is no copy of the page is on swap device. At that time, what it's supposed to do, that when whatever the page which is getting swapped out has to be copied inside your swap device along with the physical address, virtual address details. The second possibility is copy of the pages on swap device and same content in its in-core content also. So in this situation, the same content is available in your primary memory as well as in your swap device. So the content which is available in the primary memory will get erased off, that will be vanished from your primary memory, and no changes will happen in your secondary memory, that is swap device. In the third possibility is copy of the pages on swap but different in its in-core content. So that content copy is different from the swap space. That means there is some modification happen in the in-core copy. So in-core copy is a recent copy, so that has to be stored inside the swap device. So whatever is available in the swap device, that data will be erased off. The swap data will be erased, and the in-core copy will be copied into data will be copied into the swap device, and that's how it will be maintained. So there is more fragmentation on swaps page in. So whenever swapping page in, some fragmentation may happen, and that can be managed by the page stealer process. And next topic is page fault. We know what is a page fault, what incurs a page fault. So page fault is occurring whenever a page is on demand and the page is not available in the working set. So that is called as a page fault. So page fault, whenever page fault happens, the page will be loaded from the secondary memory, that means from the swap device to the working set, and then the page fault will be satisfied. It will be recovered, and then the process will continue to execute. So there are two types of page fault. One is validity fault, another one is protection fault. So validity fault and protection fault, whenever such fault happens, the fault handlers read a page from the disk to memory. The fault handler will take care of the process. So validity fault handler, if a process attempts to access a page that validity bit is 0, that is called validity page fault. So whenever it is trying to access a page which is not valid or which is illegal, so that time we'll get a validity fault. So then the validity fault handler will find the page table entry and the disk block descriptor of the page, and then it will check for any segmentation violation. When there is no record on the disk block descriptor, then that required page from that memory will be loaded, and then the particular valid default will be recovered. That valid default will be solved. So this is how validity default handler is doing. Whenever a process is trying to access a page, when the validity bit is 0, and these are the 5 states of page fault, like on a swap device and not in memory. So the process particular page is on swap device but it is not in the memory, that will incur validity page fault. And on the free page list in memory, free page list means whenever the same content is available in your primary memory as well as in the swap space, the page which is available in primary memory will be added to the free page list. Free page list means it will reset the validity bit to 0. So at that time the content is not valid, so that copy has to be taken from your swap device. And when it is in a executable file, so executable file has to be loaded, only then we can access a particular page, then marked as demand 0 and marked as demand fill. So demand 0 and demand fill is the initial steps whenever we are initializing a working set. For example, if the working set window size is 5, so 5 pages can be loaded. So demand 0 means initially that particular window size will be set as 0. There is no pages loaded into the working set window size. For example, in this example, initially the window size is 5, but when beginning of the system, during the initialization of the system, or during the first execution of the system, there is no pages are loaded into the memory. So on demand, first 24 is required, so 24 is loaded, 15 is required, 15 is loaded, 18 is required, 18 is loaded. So on demand the pages are loaded. So demand fill means keeping the window size empty, and on demand the pages will be filled. And demand 0 means keeping the window size full, keeping the working set full. If it is 5, load the 5 pages, load some random 5 pages, and if it is 4, load some random 4 pages for a particular process, and then start executing. So that is what demand fill and demand 0. Demand 0 means starting with a empty working set, demand fill means starting with full working set. The next one is protection fault handler. Protection fault handler will happen whenever process accessed validity page, but the page did not permit access. That means we have read permission and write permission for each and every page. When there is not enough permission, when the particular page we can't access a page, then this protection fault will happen. So when attempts to write a page, that copy on write is set. So copy on write is means whenever fork is executing, whenever a changes is happening on the page, it has to be copied to the new page. When that is happening, the protection fault will happen, and find another region and page table entry, then locks the region. So it will search for another region and it is locking the region. Then after finish, it set modify bit and protection bit, but clears the copy on write bit so that the content can be modified. So these are the two applications of demand paging. So demand paging can be used on this less sophisticated hardware, where we can set the hardware bits. So whenever that such bits are on or off, we can modify the bits. Whenever it is off, we can't modify the bits. Whenever it is on, we can modify the bits. So that makes this protection fault handler easy. And then we can use the hybrid system with swapping and demand paging. So we know what is swapping and what is demand paging. So swapping, we know there is a problem called thrashing, but whenever we are using a hybrid system which supports both swapping and demand paging, so we can avoid thrashing problem. So thrashing problem, we know that ready to run process is swapped out and it is not getting a chance to get executed. So the swapper process swaps out entire process until available memory exceeds the higher watermark. So there is another issue in the swap demand paging. That means when it reaches a lower watermark, all the pages which are aged will be swapped out, and then it will be swapped out until it reaches higher watermark. So that is another problem in demand paging. So that will also be satisfied by using or recovered by using this swapping and demand paging hybrid system. So this slows down the system fault rate and reduces the thrashing. So that is how the swapping and demand paging works, and we can, whenever we are using a swapping and demand paging system, so these are the advantages and disadvantages of every swapping and demand paging. So thank you. If you have any doubts, you can comment on the video in the Google Classroom as well as in the YouTube platform. Thank you.